that is this question is a really good question to understand exactly what momentum in two dimensions is. So our question is, the question is that curling is a sport played on ice. Players slide stones made of granite along the ice. The photograph shows two of the stones. Each stone has a mass of 19.1 kilograms. The player slides a stone at a velocity of 1.7 meters per second towards a stationary zone. The stones collide. So the initial collision before the momentum, we are only seeing momentum in the horizontal direction. Before the collision, momentum is only horizontally because the object number 2 is stationary and object number 1 is traveling horizontally. So we are only dealing with momentum in the horizontal direction. Now, the stones collide. After collision, both the stones move off as shown below. So after the collision has happened, that is when the stones are now moving in completely different directions. And they're moving in different directions. Along with that, they're also traveling at different angles to the horizontal. They're saying show that our velocity v is about 1.3 meters per second. For this, we are obviously going to have to use the concept of momentum before the collision and momentum after the collision, right? So if we talk about momentum before the collision, I think figuring out the momentum before the collision is not going to be hard because like I said, the mass is 19.1, yeah, okay. Because like I said, in momentum before the collision, for momentum before the collision, what is going to be happening that the momentum before the collision is just in the horizontal direction. So when we're going to go ahead and solve this question, we can talk about conservation of momentum. Okay. Now, think of it this way. Initially, before the collision, momentum is only in the horizontal direction. After the collision, we have velocity acting at different angles. Okay. In fact, don't forget about momentum for now. Let's talk about just specifically velocity. Before the collision, the velocity is acting horizontally. There is no vertical component. The only component is the horizontal component. After collision, we have a horizontal component as well as a vertical component. Similarly, a horizontal component as well as a vertical component. Okay. Now, what is going to happen that since the formula of momentum is equals to mass into velocity. So if I take the mass and I multiply it by the horizontal component, I am calculating horizontal momentum. If I take the mass and I multiply it by the vertical component of velocity, I am calculating the vertical momentum. Right? This is what I meant by momentums have different components. That's what I meant. So because velocity can have a horizontal component, so if I use the horizontal component of velocity for my calculations, I am calculating the horizontal momentum, the component of momentum in the horizontal direction. Similarly, if I use the vertical component of velocity, I am getting the momentum in the vertical component, right? Now, in this particular situation, remember this. Momentum before the collision has to be equal to the momentum after the collision. What does that mean? That means whatever momentum is before the collision. Before the collision, we only have horizontal momentum, right? Before the collision, we only have horizontal momentum. So after the collision, we should only have horizontal momentum. That means the horizontal component of momentum before the collision should be equal to the horizontal component of momentum after the collision. And if you look at our vector diagram, if you look at the diagram I've drawn, you can see that. you can see that the horizontal components are both pointing in the same direction, meaning that we can add up the momentum in the horizontal direction. The momentum in the vertical direction, if you take a look at the diagram, they're pointing in opposite directions, meaning that these two will cancel each other out. The vertical component of momentum for ball 1 as well as ball 2, or stone 1 and stone 2. The vertical component will cancel each other out for both the stones. Only horizontal component is going to be there. And that follows logic because before the collision, we also had only the horizontal component. There was no vertical component. Momentum before has to be equal to momentum after. So whatever is the momentum before, momentum after has to be the same. So if momentum before the collision was only in the horizontal component, that means momentum after the collision is also going to be in the horizontal component. And if we draw the vector diagram, we can see that the vertical components are canceling each other out. Hence, even after the collision, the vertical components are canceling each other out. So there is no resultant vertical momentum. The only momentum there is the resultant horizontal momentum. Are you following me so far? Is this making sense?
Yeah.
All right. So we can use this basis to do the calculation. There are two ways that I can think of how I can do the calculations. I'll go over both of them with you. So first thing is first, we can figure out the momentum before collision. Momentum before the collision is obviously going to be easy to determine. Momentum before, what's wrong? Momentum before is 1.7 multiplied by 19.1. So we are going to get 1.7 multiplied by 19.1, 32.47. This momentum before has to be equal to momentum after, right? So we don't have to worry about the vertical component. Like I said, we only have to concern ourselves with the horizontal component. So that means that I'm going to do M V1 plus V2. Why can I do V1 plus V2? Why can I take mass as common? The reason I can take mass as common is because they both have the same weight, right? Since they both have the same weight, I can take mass as common. So 19.1 V1, the velocity of stone number 1 is going to be 0.87. This is 50 degrees. 0.87 cos 50. Correct me if I am wrong, but I think it will be cos 50. Similarly, if I want to find the horizontal component of the object number 2 or stone number 2, that is going to be plus V cos 30. And then we can go ahead and we can solve for velocity because we know that momentum before the collision is equals to momentum after the collision. So if we go ahead and we solve for our V, 32.47 is equals to 19.1 bracket 0.87 cos 50. It gives us 0.56. 0.56 plus we have V cos 30. So cos 30 gives us 0.86. So we get 0.86 V. And then if we solve for V, so our answer comes out as 32.41 divided by 19.1. And then we get 1.69 as our answer. After we get 1.69 as our answer, so we are going to have to subtract. We're going to have to do 0.56 minus 1.69. And then divide the answer with 0.86. So your final velocity is going to come out as 1.32 meters per second, right? So this is how you can go ahead, and this is how you can solve or figure out how to find the velocity, right? And that's exactly what we had to do. We had to show that v is about 1.3 meters per second. This is what momentum in two directions is. That whatever momentum is there before the collision, momentum after the collision has to be the same. So over here, we only had to deal with momentum in the horizontal component. So in the horizontal components, we can figure out the momentum of object number 1 simply by multiplying the mass with the horizontal component. So 0.87 cos 50. Similarly, over here, momentum of object 2 after the collision in the horizontal direction. In the horizontal direction is going to be, again, mass multiplied by v cos theta. And hence, you can find the momentum in the horizontal direction. Once you have found the momentum in the horizontal direction, it has to be equal to the momentum before the collision. And then the rest of it is algebraical solution. There's one more way of solving the question. We know that the momentum in the vertical direction of both the objects has to be equal to each other. It has to be. If it was not, then we would have momentum before the collision. Vertically, momentum before the collision is 0. So momentum vertically afterwards should also be 0. Before and after should be equal. So vertically afterwards also, the momentum should be 0. Hence, we can be absolutely sure that the vertical component of both the velocities are equal to each other. So a shorter way of doing this, I think, one second, is that you can also do 0.87 sine 50, right? And then you can go ahead and divide it by sine 30. So if you do that, again, your answer comes out to be 1.33. So you're going to get the same answer that way. So an easy way of solving it is, obviously, this is the what the first idea that came in my mind is that we know that the vertical component of both the stones are equal to each other. So we can obviously do 0.87 sine 50 is equals to v sine 30 and quickly do the calculations. But there are times where you cannot be completely sure that these two components are equal to each other, right? It depends upon how the question is provided to you. In this case, we were absolutely sure because there was no vertical component before the collision. If, for example, the stationary stone was not stationary, it was moving vertically. In that case, there would be vertical component present, right? In that case, there would be a vertical component present after the collision, and these two would not be equal to each other. So the second way of solving it is a bit situation based. It depends upon the situation. So because there was no vertical component initially before the collision, I knew that after the collision, they should also sum out to be 0. They should also give me the total of 0. Hence, I could use that easy way of solving it. But if there was vertical component of momentum before the collision, you could not make these two equal to each other. In that case, you would have to do the entire calculations like I discussed with you previously, where momentum before is equal to momentum after, and then you solve for velocity. I hope it's making sense, right? How you're going to be solving questions like these?
So you essentially have to split the vertical and horizontal component of momentum.
Yes. Yes.
So then,
Go on.
So then the vertical component of momentum before the collision is equal to the vertical momentum after the collision, and same thing with horizontal.
Yes, absolutely correct. And
yeah,
if you're ever
and
if you're ever asked to find the resultant momentum by yourself, right? So in that case, what you'll do is that you'll first find the vertical component of momentum after the collision, horizontal component of momentum after the collision, and then use Pythagoras theorem and a vector diagram to find the result, right? That would be the resultant momentum. So this momentum that we're using is just in the horizontal direction. If over here there is
0.87 times, so 0.87 times 19.1 would be the resultant momentum.
Yes, absolutely correct. And if because you see a lot of vector questions related to it, sometimes they do not give you the velocity, they will directly provide you with the horizontal and vertical component of the momentum. So in that case, you have to make a vector diagram and solve the vector diagram by using Pythagoras theorem. So the resultant momentum is going to be exactly. So the resultant momentum is going to be 19.1 multiplied by 0.87. And if you resolve the horizontal component and the vertical component, like if you make a vector diagram, you'll get exactly the same answer.
That would be the resulting momentum of
Yes,
the
exactly.
number one.
Absolutely correct. Okay. I think the second part of the question, you can go ahead and attempt it yourself. Deduce whether the collision was elastic. Your answer should include a calculation.
Okay, can you go back up now?
Yes,
I
this
think
is
I know
another,
what
yeah, this is another scenario. Okay, first you solve it and then I'll say what I want.
I think I have the answer.
Yes, go ahead.
I think it's not elastic.
Yes, it is not an elastic collision. Can you give me a reasoning as to why it's not an elastic collision?
I calculated the kinetic energy before the
Yes,
collision, and then after the collision, they weren't
correct.
equal.
And what did you get before and what did you get after?
Before I got 27.6,
Mm-hmm.
and then
And
after
after?
I got 24.1.
Yeah, absolutely correct. This is
But
another reason. Yeah, go on.
I'm still not like completely sure of what I did.
Okay. So, um, what you did is basically all you have to do is calculate the kinetic energy using the formula. So if we talk about kinetic energy before the formula, before the collision, okay? So the kinetic energy before the collision is half mv square. Half, the mass is 19.1 and the velocity is 1.7. We don't have to worry about stone number 2 or the kinetic energy possessed by the stone number 2 because that is stationary, right? So you simply calculate the numerical value of kinetic energy before the collision. After you have done this, you will now calculate the kinetic energy after the collision. After the
Why didn't I
collision,
take the velocity as the horizontal component?
because energy is not a vector quantity, energy is a scalar quantity. So the direction is not important. That's why. Because energy is not a vector quantity. So we don't have to worry about the horizontal direction or the vertical direction.
Yeah, I see now.
Since momentum is a vector quantity, so we are concerned with the vertical and horizontal component. That's the main reason. So that's why you don't have to worry about the vertical and horizontal component. And that is also the reason why I advise using kinetic energy to determine if the collision is elastic or inelastic. Because in these scenarios, if you decide to use the formula speed of approach one, the one I told you, it can get a bit complicated because there are vertical components and horizontal components, and that makes it just, uh, increases the chances of making mistakes and errors. It's much simpler to just input the values in the kinetic energy formula and calculate direct. Do you understand? Do you get it now? Like I think that was the confusion that you had whether to use the components or
Yeah.
not, right? Like that's clear now.
Yeah. Can I try another
Okay,
question? Just
yes, I actually do. I want you to try another question as well. Just give me 1 minute. Hold on. Let me open it up 1 second. Okay, here's a quite a similar question. In
yeah, I'll try it.
1930,
I'll try it by myself and then.
all right, fine. Let me know when you're done reading the question. I'll scroll down to like where the actual question is.
Okay. You can show me the question now.
Let me know if you want me to scroll back in the diagram.
You can go back up now. I'm having like a bit of difficulty finding the angle, but I did find the momentum of the proton after the collision.
Okay, perfect. Okay, so I'll go over it with you. When we are going to go ahead, so if we obviously you can see that once again we have a familiar situation in the sense that the vertical component is again going to be equal to each other. So the main thing that, there we go. Okay, so we already have the momentum of the alpha particle before the collision, and we have the momentum of the alpha particle after the collision. So you are, again, if you look at the question, you know that horizontally, oh, I think I have an idea where you might be going, but I'll still go over it. Horizontally, right, we are going to resolve the momentum. So momentum before the collision in the horizontal component is 1.26 into 10 raised to the power of negative 19. Momentum after the collision for the alpha particle, we have 8.06 into 10 raised to the power of negative 20. This is momentum. That is the resultant momentum. Since we are concerned with just the horizontal momentum, so we can go ahead and take a look at the horizontal component. But just give me 1 second. So if we talk about momentum after the collision is going to be 8.06 into 10 to the power of negative 20 cos 10.2 plus the horizontal component of the momentum of the proton. Whatever the momentum of the proton is, whatever the horizontal component is, that is going to be that if I add these two values, if I add the horizontal component of the momentum of the proton to the horizontal component of the momentum of alpha particle, that should be equal to the momentum of the alpha particle before the collision. Using this method, I can find out the horizontal component of the momentum of the proton. So if I take out my calculator, where did it? So we are going to do 8.06 into 10 raised to the power of negative 20. Multiply this by cos 10.2. This gives us 7.93 into 10 raised to the power of negative 20. So again, we subtract 1.26 into 10 raised to the power of negative 19. And from it, we are going to go ahead and we're going to subtract our answer, right? So our final momentum, this momentum that we're going to get, the horizontal component of the proton, is going to come out as 4.67 into 10 raised to the power of negative. Now, we have to go ahead and we have to figure out the vertical component. To figure out the vertical component of the proton, we can see that vertically, there is no initial momentum. That means final momentum is also equal to 0, just like in the last question. So the vertical component of alpha particle is equal to the vertical component of the proton. So that gives us 8.06 into 10 raised to the power of negative 20 multiplied by sine 10.2, whatever the value is, that is equal to the vertical component of our momentum, right? So the vertical component of the momentum of the proton is going to come out as 8.06 into 10 raised to the power of negative 20 multiplied by sine 10.2. So we get 1.43 into 10 raised to the power of negative 10. Now that we have the horizontal component and the vertical component, we can figure out the resultant by using our Pythagoras theorem. So to for the Pythagoras theorem, we can simply square both the sides and get our answer. So square the vertical component plus we are going to square the horizontal component. And then we obviously underroot the answer. So when you do that, your final momentum is going to come out as 4.88 into 10 raised to the power of negative. If you've managed to solve it this far, the next step is super easy. This is our triangle, vector triangle, right? In our vector triangle, the angle with the horizontal is theta. We know that the vertical component is 1.43 into 10 raised to the power of negative 20. We know that the horizontal component is 4.67 into 10 raised to the power of negative 30. And now we are also aware that the hypotenuse is 4.88 into 10 raised to the power of negative 20. You can solve this, find the angle using trigonometry. So either you can go for tan theta, cos theta, sine theta, whatever you prefer, right? So for example, if you decide to do cos theta, you will do 4.67 divided by 4.88, and then you will simply do cos inverse. So finally, your angle theta comes out to be 16.8, which can be rounded off to 17 degrees. The main trick, final trick is when you're getting the resultant momentum, you're making a vector triangle, right? So in that vector triangle, you have the base, you have the adjacent, and the hypotenuse is the resultant momentum. You will get the resultant momentum by using Pythagoras theorem because it's a right angle triangle. And to find the angle theta, you can simply use any trigonometric ratio that you prefer. Making sense? I hope that clears things up a bit.
Yeah, I made a big mistake. That's why I went wrong.
Okay, great. So as long as you know where you were going wrong,
Yeah.
that's perfect.
Would there ever be questions where they ask you for, like before the collision, there'd also be like a vertical component as well?
Yeah, there can be questions where the vertical component is also present before the collision. But in that case, that doesn't complicate anything, right? So for
You
example,
just
if you
have
go back,
something else.
yes, it's just an extra step. So over here, do you see how we did momentum before is equal to momentum after? And that's how we
Yeah.
solve the question. You'll do the same thing for the vertical component. You'll do momentum before is equal to momentum after. So you'll do the same thing. That's not going to affect your results whatsoever.
Yeah, I see now.
Okay, the next part, I believe, of this question is about you have to deduce whether the collision is elastic or not. Mass of an alpha particle is 6.64 into 10 is to the power of negative 27. Okay, so in questions like these, where sometimes, like not sometimes, often my students get confused, is that to find the, they know that if you want to find out if the collision is elastic, you'll calculate the kinetic energy. Where they get confused is the mass. Because like you can see that the mass of proton is not mentioned. So in this case, please always remember if you go right towards the end of your question paper, right? Not only are all of these formulas going to be given to you, but along with these formulas, they have also given you a lot of the values. So in this particular case, you can see that the mass of the proton is mentioned here towards the end of the paper. So whenever you're dealing with particle physics, this is usually one of the problem that happens, that oftentimes the students get really confused because they don't have the mass. Then they try to figure out other ways of calculating kinetic energy, which is a very simple thing to do. So in particle physics, sometimes for particles like the mass of an electron, mass of proton, unified atomic mass, which I will teach you later, these are usually mentioned towards the end of the paper. So the mass of a proton is 1.67 into 10 raised to the power of negative 27. This is where you will get the value from. This is the tricky part. If you know that this is where you're supposed to get the value for, the rest of it is quite simple because all you have to do is simply calculate the kinetic energy. So would you like to go ahead, give this a try, calculate the kinetic energy and deduce whether the collision is elastic or not?
Yeah, I'll do it now.
Ashwish, I don't mean to interrupt while you're solving, but I was just going to say if you're going through the route of finding velocity first and then using the formula, so that's a very long and complicated route. There is a much quicker and
I
faster
did
way to
think
do it.
of that. I did the one we learned yesterday
Yes,
with
good. That's yes.
p squared over 2m.
Yes, exactly. That's exactly what I was going to say. Don't bother going through half mv square for this. Use the momentum formula because you already have the momentum. You don't need to find the velocity.
Yeah, I'm almost done now.
Perfect.
Yeah, I got that the collision was elastic.
All right. You are getting that the collision is elastic. Can I figure out, can you tell me what kinetic energy you're getting before and after?
Yeah, 1.2 times 10 to the power minus 12.
Right. That is before and what's after?
The same thing, like 1.2 times 10
Yeah,
to the
yeah, yeah.
power
Oh,
minus
yeah,
12.
yeah, 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 yeah. That is absolutely correct. That's fine. Perfect. Okay, Ashwish, I think we can go ahead and stop it over here for today. And then we can we'll continue with the questions on the topic in the next class. Okay?
Yeah, thank you, miss. Have a good day.
Have a good day, Ashwish. See you.